Top 15 stones with unbelievable natural patterns. Not every stone tells its story with brilliance or fire. Some carry their record in silence, in bands, orbs, plumes, and fractures left unchanged for millions, even billions of years. These are not decorations. They are structures formed from pressure, chemistry, and time, preserved exactly as they were when they formed. In this journey, 15 specimens are brought forward. Each one presents a pattern the Earth never repeated. Stripes laid down in ancient sediments, microbial colonies fossilized into stone, mineral sprays frozen in quartz, or webs of manganese ceiling fractures. None were designed, none were predicted. All remain as the planet left them. Welcome to Tops, where every story is drawn from the Earth itself. We begin with the first. Ranked 15th, Fordite, the only stone born from factory fire and paint. The stones you've seen so far were carved by geological time. However, the next one was formed by machinery and forgotten until the process that created it no longer existed. It began with overspray, not from an artist's hand, but from the paint booths of Detroit's auto factories in the mid-20th century. Day after day, hundreds of car bodies, Fords, Chevrolets, Oldsmobiles, passed through suspended rail systems where high-powered sprayers coated them in layer after layer of enamel. Crimson, olive green, pearl white, gunmetal blue. Each vehicle brought its own palette, each year its own formula. And yet, the excess paint didn't just vanish. It fell onto the metal racks below and stayed there, accumulating silently. What happened next wasn't part of any plan. As the production lines ran hotter and longer, these layers of paint were repeatedly baked in industrial ovens, cured, hardened, and then resprayed. The result? Thick masses of fused paint, built up over months, then years. Hundreds of layers, each one corresponding to a specific model, a specific moment in manufacturing time. It wasn't called anything back then, just build up. Waste, sometimes chipped off, sometimes ignored and never documented. That changed when factory workers in the 1980s began dismantling older paint booths. What they found clinging to the hardware didn't look like trash. Sliced open, the hardened paint blocks revealed patterns so intricate that they resembled natural gemstones. Waves of color swirled across the surface like topographic maps. Concentric rings mimicked agates. Others displayed spirals, bursts, or jagged lines, all created by the inherent randomness of the production process. Collectors called it Fordite, borrowing the name from the automaker most associated with the region. Others called it Detroit Agate, although it was neither an agate nor a stone. It was hardened enamel, built from automotive paint, crystallized only through heat and repetition. By the late 1990s, lapidary artists began cutting and polishing Fordite just as they would jasper or onyx. The results were startling. Unlike traditional gemstones, Fordite didn't have to be imagined under the earth. Its provenance was traceable. A multicolored piece might reveal the color order used in 1970s Dodge Challengers. A solid navy gray base with a blood red overlay might link directly to GM's 1981 production run. Every layer encoded a sequence. Every curve was the accidental archive of a machine's memory. But Fordite is finite. The process that created it, spray paint booths with high waste and multiple curing cycles, no longer exists. Modern car factories utilize electrostatic painting systems that minimize overspray, eliminate rack buildup, and prevent repeat firing. No new Fordites are being made. What remains is what survived the cleanup. Scrap salvage from paint lines, ductwork, or industrial salvage yards. Every piece is a geological impossibility born from mechanical routine. And unlike natural stones, Fordite isn't judged by carat weight, clarity, or luster. Its value lies in the timeline it preserves. For some, it's jewelry. For others, it's Detroit's accidental fossil record, a visible history of mid-century American industry. It appears in no gemological database. It has no crystal system, no lattice, no cleavage plane, and yet Fordite is cataloged, tagged, sold, stored. A typical listing includes origin facility, production year, and known paint layers. red, ivory, primer, and chrome yellow. Some samples are even matched to archived vehicle color charts from the National Automotive History Collection. Ranked 14th, malachite, geometry in stone, laid layer by layer. It doesn't sparkle, it doesn't bend the light, it doesn't beg for attention, and yet malachite holds the gaze longer than most transparent stones. The mineral is dense, translucent, and opaque. Its green isn't soft, it's saturated, not in hue but in weight. Look once and the eye sees color. Look again and the eye sees structure. Look longer and it sees a pattern too precise to be random, but too irregular to be designed. Malachite forms in the oxidized zones of copper mines, where groundwater mixes with carbonate and copper ions and encounters cracks in the bedrock. As the water moves in, it deposits thin layers of copper carbonate hydroxide along the edges of the cavities. These layers harden, but only temporarily. As conditions change, the process repeats. New layers form on top of old ones, like tree rings without trees, without seasons, without growth. Each line is a trace of hydrochemical activity. Over time, enough layers form a mass, and sometimes that mass is large enough to cut. A single slab of malachite can contain dozens, even hundreds, of concentric or parallel bands. Some flow like ink. Others curve like waves against an invisible shore. The pattern moves without moving, a two-dimensional archive of a fluid history, stabilized in a coppery green. No two pieces are alike. The bands curve without repeating. Some are sharp, others are blurred without symmetry. Although the formation is chemical, the result appears biological. To the naked eye, it may appear to be plant matter under a microscope, or a magnetic field frozen in a mineral form, but in fact it is not. It's simply what copper does when it has enough time and nowhere else to go. The finest malachite originates from two regions, Katanga in the Democratic Republic of the Congo and the Ural Mountains in Russia. From the Congo came the massive, dense boulders solid enough to be sculpted. From the Urals came a new order, stones so finely patterned that they were used as architectural materials. In St. Petersburg, entire columns and altar panels were clad in uniform malachite, cut and polished not for jewelry but for architecture. This was not decoration, it was an enhancement. A mineral that knew nothing of symmetry had been repurposed into a mathematical spatial system. In the 18th and 19th centuries, Imperial Russian workshops saw malachite as evidence that the Earth could create geometry, unrefined, untrained, but ready. They didn't carve it into cabochons. They hammered it, mirrored it, laid it flat on wood and bronze. The malachite became the surface, not the background, but the foreground. Today, most of what comes to market is sliced, pieced together, or glued. The big blocks are gone, mineralized, stored, or sold decades ago. What remains are fragments, shaped for retail sale. However, in some institutions, such as mineralogical, artistic, or state-run, the original slabs remain, and they don't fade. Malachite is sensitive to light, acid, and temperature. But it is not time-sensitive. Its patterns don't disintegrate. It doesn't oxidize or shift. What has been laid down remains where it is. Copper, carbonate, hydroxide, repetition. When viewed in soft light, the surface of a complete malachite facet appears to be in motion. The eye follows one curve, then another, and then loses its place, starting over. There is no center, no axis. Only the illusion of expansion, inward and outward, is controlled by the width of the band and the person's attention. The stone itself does nothing. It lies still. It reflects nothing. It tells no story. But the pattern does. Ranked 13th, lace agate, a pattern that refuses to repeat. There is no center, no point of origin, no rotational axis. Lace agate does not build from the inside out. It builds in segments, in pulses, each one beginning where the last one broke. Its structure is chalcedony, but its behavior is different. While other agates tend towards symmetry, lace agate disrupts it. The layers twist, re-enter themselves, collapse, and restart. Sometimes the flow is linear, sometimes spiral, sometimes both at once. It forms in voids, often in limestone cavities, where mineral-rich fluids enter, pause, leave behind material, and retreat. Each band is the mark of one such interruption. The process is neither fast nor stable. That instability is visible in the stone's face. At a glance, it resembles a pattern, but the deeper you look, the more it disassembles. Bands start clean, then fracture. Parallel lines drift, loop back, or vanish entirely. There is no underlying order, only persistence. The stone is not trying to create form. It is a recording disruption. In some specimens, the bands run in long, clean corridors. In others, they fold into themselves like tangled circuitry. You can follow a single line for several millimeters before it dissolves, splits, or runs headlong into another. Nothing finishes. Nothing aligns. The best examples come from Chihuahua, northern Mexico, a region where limestone meets volcanic history. The silica that forms lace agate is deposited not from one fluid event, but from many, over cycles of heat, pressure, erosion, and recharge. This is not a single narrative. It is layered noise held together by mineral adhesion. Unlike more prized agates, lace agate has no optical qualities. It does not refract, it does not shimmer. Its value is not in clarity, but in contradiction. Fine-grained quartz behaving like a freehand sketch. It was not always considered valuable. For decades, it was cut into beads, tumbled into mixed parcels, and sold without classification. Its irregularity made it difficult to polish, harder to match, and impossible to pair in symmetrical sets. Jewelers disliked it. Collectors overlooked it. That changed when macro photography and high-contrast scanning entered the mineral market. Under proper lighting, the internal logic of lace agate became visible, and viewers realized that what looked chaotic was in fact traceable. Not understandable, but traceable. Still, the stone resists explanation. No two slabs from the same boulder ever match. In most cases, the reverse side of a cut face bears no resemblance to the front. Thin sections viewed under cross-polarized light reveal further disruption. Grain boundaries, growth terminations, and fluid inclusions. None of these align with the bands on the surface. There are no myths surrounding lace agate, no ancient symbolism, no religious use. Its patterns are not referenced in early mineral texts. It has no assigned metaphysical properties. It is not linked to any season, zodiac, or ritual. It is a mineral record of instability, that is all. Some slabs have been digitized, others sit in drawers, labeled but not categorized. The stone cannot be sorted by color, nor grouped by grain. There are red bands, gray voids, ochre folds. None of them repeats. When cut thin and polished, the surface appears deliberate. That is the illusion. The bands were not placed, they were left. The face of a fine lace agate cannot be predicted from the outside. You cut into it, you find out, then you stop. And what remains is not the final layer, only the one the blade reached. Ranked 12th. Septarian Nodule. Fractured, filled, then forgotten. It appears cracked. Yellow-white veins divide the brownish mass into irregular polygons, some as wide as a palm, others finer than a fingernail. The surface suggests breakage, but the structure is solid. This is not damage. This is a resolution. Septarian nodules are whole objects made from two events, rupture and repair. The lines you see are not fault lines. They are healed fractures, mineralized, filled, sealed. But to understand them, you begin from what they are now, then subtract. The nodule resembles a map without orientation on its surface. Its veins form no center, no perimeter. They cross one another, shift direction, taper, double back. In some nodules, they branch sharply. In others, they radiate from a central hub. But the system has no symmetry. What it has is history. The outer shell is composed of limestone, which is silty and compact. Within it lies hardened sediment, marine mud layered with organic calcium, deposited in shallow sea basins millions of years ago. This mud compressed slowly. As water escaped, the internal mass shrank, but not smoothly. Internal stress built up until the solid core cracked. This was not violent. It didn't explode or shatter. The fractures opened gradually, responding to stress differentials across the mass. The result, a network of hollow veins running through what had once been a uniform core. Then came the second phase, mineral-rich fluids carrying calcite, aragonite, and sometimes barite entered the voids. These fluids did not flood the stone. They crept in, depositing thin crystalline layers along fracture walls. Some are filled, others left partial gaps or pockets of trapped gas. The infilling was irregular, dependent on both access and saturation. In some environments, the veins took on deep yellow tones. In others, they hardened bone white. The outer matrix remained dull, a mix of Earth's browns, grays, and ochres. But the contrast sharpened with each new layer of calcite. Eventually, the network became visible through weathering. Later, it was exposed by excavation, and finally by a saw. The internal pattern could not be predicted. There was no way to know, from the exterior, how the fracture system had formed. Only by cutting could the structure be revealed. And by then, the process had already come to an end. Today, the stone is sometimes marketed as dragonstone, a term derived from the visual similarity between its cracked surface and reptilian scales. However, the name is relatively recent, having been invented for commercial purposes. It carries no geological meaning. It reflects only appearance, not origin. There are no myths associated with Septarian nodules, no recorded uses in pre-modern cultures. Their significance lies in sequence, not symbolism. Each nodule is a complete record of internal failure and correction. It is not a scar. It is a map of what broke and what sealed. From a collector's view, the value lies in contrast: strong lines, sharp transitions, closed cavities. From a geological perspective, the sequence of events is as follows: deposition, compaction, dehydration, fracture, mineralization, lithification, exposure, and discovery. Reverse those: discovery, exposure, lithification, mineralization, fracture, dehydration, compaction, deposition. Stop there. That's where it started. Ranked 11th. Ocean jasper. Every cut reveals, then ends. You don't find the pattern by looking at the surface. You see it by cutting and cutting again. Ocean jasper doesn't offer a single face. It changes with each section. Circles in one slice, waves in the next. Diffuse textures beyond that. No orientation is correct. No orientation is wrong. Every exposure is partial. Every exposure is different. The stone is composed of microcrystalline quartz, chalcedony, but what defines it is not chemistry, it's structure. More precisely, interruption in structure. The orbicular forms, the banded rings, the radiating plumes, all of them are the result of silica depositing through pulsing hydrothermal systems. These systems were unstable. Their chemistry changed constantly. Iron, calcium, and manganese each left a trace. Each movement shifted the form. The result is not chaos, but neither is it regularity. It is an accumulated inconsistency, stabilized only by the passage of time. Ocean jasper comes from only one known place, a coastal deposit near Maravato in northwestern Madagascar. It sits at the literal edge, not of land and sea, but of access and denial. The material can only be quarried at low tide. For much of the day, it's unreachable. When first rediscovered in 1999, miners had to plan extraction by the hour. Some days yielded nothing. Others produced slabs of unpredictable complexity. What makes the stone distinct is not just where it forms, but how. The silica was not deposited in open cavities. It moved through rock already solid. The orbs did not grow from a center. They emerged from multiple diffusion fronts, pushing against one another, then halting. The stone is a record of competing directions. Some pieces show dense orbicular patterning, hundreds of small circles packed into a single section. Others reveal banded arcs, cutting across clusters like waves frozen mid-break. Some have voids. Others are moss-like inclusion zones. The transitions are abrupt. There are no gradients, no foreshadowing, only the moment the chemistry changed. In its short commercial history, ocean jasper was always problematic. Buyers wanted consistency, retailers wanted predictability. This material offered neither. A single boulder could yield a dozen unrelated appearances. Dealers sliced, scanned, and labeled the products. But every cut reset the expectation. There is no known alternative deposit. After several years of limited production, the primary site reached exhaustion. The ocean resumed its claim. No wall was built, no gate installed, no sign posted. The waves returned. That was enough. What remains now circulates in fragments, cut slabs in private collections, polished faces in drawers, archived pieces in academic holdings. A few were never sliced, left whole, unopened, the potential variations hidden beneath a rind of rough matrix. Some cutters refused to open them, not out of reverence, out of decision, because once cut, the piece is no longer hypothetical. The moment is fixed. The variation ends. The unknown collapses into a single face. Ocean jasper isn't rare by composition. It's rare by resolution. Not how much of it exists, but how little of it can ever be known completely. Collectors sometimes speak of the good side, but no side is final. No side is complete. Each is just the latest surface to be revealed, and eventually the decision is made not to cut further, not because there's nothing left, but because there's nothing more to say. Ranked 10th. Moss agate, a pattern that looks alive, but isn't. What grows inside is not growth. What appears to be motion is not actually moving. Moss agate displays branching forms, sharp, fine, interconnected, that mimic the structure of plants, veins, or roots. But what you're looking at is not biological. It's a crystallographic deviation. Mineral movement that stopped long before it could ever resemble life. These are dendrites, inclusions formed when trace elements like manganese or iron infiltrate silica-rich gel and begin to precipitate. The chemical balance shifts, the ions deposit, lines appear, they follow no code, and yet to the eye they are recognizable. Each dendrite branches according to thermodynamic thresholds, pressure gradients, and saturation points. None of them grows, none of them reach, but they spread. As they do, they trace forms we associate with organisms, not because they intend to, but because biology, too, must follow rules of diffusion. The similarity is a coincidence. The structure is not alive. Moss agate is quartz, translucent, often whitish or gray, sometimes transparent. The inclusions are internal. They cannot be felt on the surface. They don't interrupt the polish. They don't change the refractive index. What they do is define depth. From Gujarat to Montana, each region's moss agate carries a different palette. In India, clear matrices with black dendrites. In Oregon, misty grounds, olive greens, rust reds. In Wyoming, snow-colored quartz with almost calligraphic inclusions. Some slabs resemble landscapes, others X-rays. There is no standard view, only the tendency to resemble without becoming. No specimen is uniform. A single slice can show dense entanglement on one end and nothing on the other. No axis holds, no direction is defined. Rotate it, and the image reinterprets itself. It resists categorization. There are no central veins, no crystallographic anchors. The dendrites move through the gel state quartz before it hardens. Their distribution depends on when the fluid slowed, where it pooled, and how long it remained unstable. Cutters don't shape moss agate for brilliance. They cut for orientation, hunting for that single angle where the internal network appears suspended, as though hovering inside the stone rather than pressed flat. It's not about color. It's about density, separation, and contrast. Some pieces never show it. Others show too much. Dendrites so dense they erase the negative space. The best hold tension, enough space to isolate from, enough intersection to imply intention, but never enough to resolve it. Moss agate doesn't hold a legend. It wasn't ritually used. It wasn't named by emperors or mined for prestige. Its value is in what it resembles, not what it is. And even that resemblance is unintentional. When collectors describe it, they often default to comparison. Forest in stone, frozen lightning, veins of earth. But these are only approximations, because what's inside isn't a forest. isn't nerve, isn't root. It is only a mineral phase disturbance, fixed in place, immobile, irreversible. And when the dendrites fade, as they sometimes do, the quartz continues, silent, unpatterned, indifferent. The final third of a polished slab might contain nothing. No black, no green, no red, just glassy chalcedony with no inclusion. No trace, no explanation. What it looks like is life. What it ends in is absence. Ranked ninth, Pietersite, the stone that shifts as you watch. A burnished gold thread flashes, arcs left, and vanishes. Shifts slightly. Now it's deep navy, static, silent. Move again. A vertical blade of red cuts through the field. None of these were visible a moment ago. All of them are real. This is Pietersite, a stone that does not contain color, but disperses it. Not in sequence, but in defiance. Structurally, Pietersite is quartz, but within it are fractured chrysotolite fibers. Once straight mineral strands, now broken, twisted, and fossilized under tectonic pressure. These fibers were replaced by silica, but the violence of their rupture remains. The result is not a pattern, it's a conflict locked in a mineral. In tiger's eye, these fibers run parallel, chatoyant ribbons that behave like silk light. Pietersite offers no such order. Its fiber fields are angled, warped, and superimposed. Light doesn't move in lines, it fractures. Namibian Pietersite is a volatile gemstone, characterized by high contrast, density, and instability. It flashes without warning. A surface that looks inert one moment ignites the next, depending only on angle and light. Chinese Pietersite exhibits distinct characteristics, broader zones and warmer tones, yet retains the same structural inconsistency. Neither version repeats itself. Polished Pietersite doesn't shimmer, it pulses. The viewer's eye triggers the reaction. As you move, so does the stone. Not physically, but visually. The light doesn't sit still. The pattern doesn't stabilize. Cutting Pietersite is not about exposing symmetry. There is none. The best cuts don't chase composition, they interrupt it. The goal is not to control the light, but to destabilize it just enough that the surface reacts. Not predictably, not obediently, but perceptibly. There is no way to know what it will do next. This is why Pietersite is often misread. Photographs freeze it. Descriptions flatten it. Even video captures only one range of behavior. The experience depends on the exact alignment of the observer and their movement. The stone is silent, but its reaction is not passive. It challenges the observer's sense of continuity. What you thought was gold becomes black. What you thought was depth is surface. What you thought was static begins to shift. There are no legends tied to Pietersite, no sacred use, no symbolic lineage. Its entire significance lies in perception and how little that perception can be trusted. Some viewers see storms, others flame, some see nothing. That too is accurate. Pietersite does not offer a singular visual identity. It provides a contradiction, a surface that rejects confirmation. You think you see form, then you turn it, and the form collapses. What you see is not the stone. What you see is what the stone allowed, for that second, before taking it back. Ranked 8th, Rhodonite, beauty, written in fractures. At first glance, Rhodonite looks simple, a field of pink, soft and matte, like porcelain cooled to silence. Cut and polished, it seems whole, a uniform surface, steady under light. Nothing appears unstable. But that is only the present state. The polished face conceals a complex network, and it is this network that defines it. Across the pink stretch, black veins cut through, angular and unyielding. Some run straight, some fracture mid-path, others branch into webs so dense that the pink looks trapped inside. These are not decorations, they are manganese oxides, locked into place along old lines of breakage. Work backward, and the story unfolds in reverse. Before the cut and polish, the surface wasn't smooth. It was raw, unrefined, the pink dulled by weathering, the veins thicker, coarse, less integrated. The fractures looked unhealed. Go further back. The stone wasn't even coherent. Under stress, it splits, geological forces pushing and pulling against its own weak points. What should have been a collapse became something else. Manganese-rich fluids infiltrated the breaks, hardening them into black seams. The fractures didn't erase themselves. They filled, sealed, and stayed visible. Further still, before the rupture, rhodonite existed as a crystalline silicate, with manganese giving it its distinct rose to red hues. It formed in metamorphic environments where pressure and heat reshaped manganese-bearing rock. The pink structure was not pure. It was interlaced with calcium, iron, and silicon, each of which contributed to its stability. Earlier still, the conditions were different. Volcanic and hydrothermal systems concentrated manganese, distributing it unevenly, laying the groundwork for instability. What became a polished stone began as a geologic compromise, holding both strength and weakness in its very chemistry. Fast forward to what we see today, Russia's Ural Mountains once supplied massive decorative blocks. In the 18th and 19th centuries, rhodonite was carved into architectural elements, reliquaries, and even sarcophagi. In South Africa and North America, smaller deposits produced cabochons and slabs. But among collectors, it's the black-webbed type that draws attention, not for purity, but for the way it holds its scars. Each specimen is unique. Some show delicate tracery, as though inked by hand. Others are almost obliterated by dense black matrices, leaving only shards of pink intact. None can be replicated. No two webs are alike. The manganese oxides follow the unpredictable path of old stress fractures. They record failure as design. Unlike transparent gems, rhodonite doesn't work with light. It doesn't bend, split, or capture it. Its beauty is structural, not optical. What you see is what was broken, what was filled, what was stabilized. Its story lies not in what it reflects, but in what it retains. Reverse the clock once more. You arrive not at perfection, but at pressure, at heat. At the moment the stone was forced apart, the webbing isn't secondary, it's primary. Without fracture, there would be no black. Without stress, no web. Rhodonite is not a record of harmony. It is a record of disruption and what followed, from a polished artifact back through rupture, back through crystal formation, and back through hydrothermal intrusion. Initially, before the break, it was uniform, ordinary. It became extraordinary only when it failed. Ranked 7th, Tiger Iron, a Precambrian archive in 3 layers. The polished face of Tiger Iron presents 3 colors, 3 textures, 3 materials. Golden bands shimmer under light. Tiger's eye. Red to brown opaque zones. Jasper. Metallic black streaks. Hematite. Together they form not a mixture, but a sequence. Tiger iron is not one mineral. It is 3, locked side by side, layer after layer. Each line you see was once an interval in the Earth's history. Silica-rich fluid deposits forming quartz, iron-rich sediments forming hematite, volcanic or hydrothermal influences stabilizing jasper. The process repeated, over and over, until the result became striped, complex, yet orderly. From a collector's perspective, it is aesthetically pleasing. From a geological perspective, it is a testament to the power of nature. The host rock is part of the Precambrian banded iron formations, estimated to be over 2 billion years old. These formations record one of Earth's most essential transitions, the Great Oxidation Event. When free oxygen accumulated in Earth's atmosphere, dissolved iron in the oceans precipitated, forming layers of hematite. Between these, silica gels deposited quartz. Later, tectonic and metamorphic forces altered parts of it into jasper and transformed the fibrous chrysotolite into quartz with chatoyancy. Tiger's eye. What you hold now is not just a stone, but a record of oxygen entering Earth's system. Jasper, hematite, quartz, a triad formed by chemical cycles repeating over geological time. Some layers stretch for meters in the outcrop. Others are millimeters thin. None is uniform. The cutting of tiger iron is less about symmetry than exposure, to reveal at least one sequence of gold, red, and black in equilibrium. Tiger iron does not refract. It does not conceal. Its surface is precisely what it is, an archive of deposition. Unlike agates or opals, there is no unpredictability here. The stripes obey deposition, not chaos. What is unpredictable is only the angle of light and how the golden bands of tiger's eye flash under movement. Most commercial tiger iron comes from Western Australia, particularly the Pilbara and Hamersley regions. These deposits are ancient, stable, and limited in quantity. There is no secondary source of equal quality. Material is abundant enough for collection, but not infinite. Culturally, tiger iron has no myths. Its value is geological. It appears in no ancient texts, no temples, no legends. Its role is to show, not to symbolize. Each polished slab is an excerpt, not the whole book, but a single page from Earth's archive. One page shows hematite as the dominant feature, while the others feature jasper. Another page glows with broad streaks of tiger's eye. No slice is comprehensive. All are fragments. The record remains open in the ground, but every piece removed becomes static, cut from the sequence. Tiger iron is not rare by chance. It is rare in context. Its story is not about scarcity, but about what it preserves. Ranked 6th, Boulder Opal, color bound to ironstone. The surface does not begin with color. It begins with mass. Ironstone, dense, brown to black, carrying the weight of millions of years. The iron is the majority, the backdrop, the anchor. Only when the surface shifts under light do interruptions appear. Streaks of blue, green, red, orange. They cut across the matrix in uneven patches, sudden and irregular. This is Boulder Opal. Unlike free opal, which can exist as nodules or seams independent of the host, Boulder Opal is inseparable from its matrix. The opal formed within fractures of ironstone, filling voids, hardening in place, and never breaking free. Its identity is dual, host and vein, solid and luminous, stone and interference. The geology is precise. Silica-rich fluids percolated through ironstone millions of years ago. In open cavities, the silica spheres settled into ordered arrays, resulting in the diffraction of light. That is where the flashes come from, not from pigment, but from structure. But the process never filled the hole. It left fragments, pockets, channels. The opal is confined, its colors bounded by the matrix that contains it. Queensland, Australia, is the only known source of Boulder Opal of this kind. The deposits extend across vast ironstone basins. Extraction is laborious. Most boulders yield only thin seams of opal, sometimes just millimeters thick. And yet, those millimeters can produce full flashes of spectral color when polished. Boulder Opal entered recognition later than black opal or white opal. For years, miners dismissed it. Too much host, too little opal. But once cutters learned that the ironstone was not waste but part of the appeal, its status shifted. The contrast became the point. The stability of the host allows thin seams to be cut without crumbling. What was once seen as a limitation became defining. The appearance is never predictable. A single boulder might hide veins of green fire inside one fracture, orange flashes in another, or nothing at all. Cutting is an act of exposure. Each slice reveals an interface, and once admitted, it cannot be undone. On the market, Boulder Opal sits between common opal and the rare black opal of Lightning Ridge. It lacks the unbroken darkness of black opal, but offers something else: individuality. No two pieces are alike, because no two fractures follow the same path. Collectors value not carat weight, but composition, how the colors in ironstone balance across the surface. The stone resists standardization. Some faces feature vast fields of blue, while others have thin lines of green. In some, the color is bold and immediate. In others, it flickers only at the right angle. The ironstone frames it all. Without it, the opal would not survive the cutting process. With it, the opal is anchored, stabilized, made visible. There are no myths around Boulder Opal, no sacred history. Its significance lies in geology and observation. It is not symbolic, it is factual. Viewed closely, the boundary is always abrupt. One side opaque, heavy with iron, lightless. The other, sudden bursts of spectral diffraction. The meeting point defines the stone. Boulder Opal is not free, it is fixed. The host and the color are the same. That surface is the specimen. And there the record stops, at the line where ironstone holds light. Ranked fifth, Chrysocolla in quartz. Color stabilized by stone. The first impression is color. A vivid blue-green, intense and concentrated. But look closer, and the surface is not Chrysocolla alone. It is quartz, transparent or milky, holding the color inside. On its own, Chrysocolla is fragile. It scratches easily, crumbles under pressure, and rarely survives cutting. That is why most Chrysocolla never enters the realm of gemstones. But when quartz surrounds it, the structure changes. The silicate network of quartz stabilizes the Chrysocolla inclusions. The result is a composite, vibrant copper silicate locked inside a durable silica frame. This is Chrysocolla in quartz, sometimes traded under the name gem silica. The process of formation begins with copper-rich fluids moving through the host rock. They deposit Chrysocolla in fractures and cavities. Later, silica-bearing solutions infiltrate the same zones, filling in around the Chrysocolla. Over time, quartz crystallizes, encasing the softer mineral. What was once unstable becomes permanent. In Arizona, the blue can be almost electric, saturated by copper, sharply defined against clear quartz. In Peru, the tones lean green, diffused through translucent chalcedony. In Israel, near the ancient copper mines of Eilat, Chrysocolla appears together with malachite and turquoise, producing mottled zones of green, blue, and black. Each region leaves its own signature. The stone resists uniformity. Some specimens are primarily composed of quartz, with faint traces of blue veining. Others are nearly solid Chrysocolla, stabilized only in part. The best show balance, rich, floating zones of color fully supported by quartz, polished to reveal both the transparency of the host and the saturation of the inclusion. Collectors distinguish between Chrysocolla masses and Chrysocolla in quartz. The latter is cuttable, polishable, and stable at a hardness of 7. The former, rarely so. What makes the gemological difference is not the copper silicate itself, but the quartz that holds it. Historically, Chrysocolla has no mythic status. It does not appear in ancient rituals. Its modern value lies in aesthetics and durability. Within the gem trade, gem silica has become a niche category. Rare, expensive in fine quality, and often mistaken for turquoise or chrysoprase by casual observers. But its identity is singular. No other material combines Chrysocolla's vivid hue with quartz's hardness in quite the same way. No two specimens are identical. Each cut reveals a new arrangement. Swirls, pools, veins, diffuse clouds of blue-green suspended in clear or milky quartz. Some stones display concentric zoning, characterized by darker Chrysocolla cores surrounded by lighter halos. Others reveal sharp boundaries where quartz abruptly overtook the copper silicate. The contrast can be delicate or stark, but never ordered. In hand, the experience is not about brilliance. Quartz does not refract like diamond. Chrysocolla does not glow from within. What you see is surface, and depth held in stillness. The color is locked, preserved, and unchanging. It is not Chrysocolla alone. It is not quartz alone. It is both inseparable. Viewed closely, the boundary is visible. Quartz, hard and clear, encased within Chrysocolla, soft and opaque. That edge defines the stone, and at that edge, the description stops. Ranked fourth, Laguna Agate. The face of Laguna Agate is circular, tight, ordered, nested. Each one is thinner than the last. Each one is a record of a pause, then a restart. Agate forms when silica-rich fluids seep into cavities of volcanic rock. In most cases, the layers are broad, loose, and inconsistent. But in Laguna Agate, the deposition is disciplined. Each band is fine, consistent, and intensely pigmented. Red into white, white into orange, orange into pink. The sequence repeats, sometimes for dozens of visible rings. No symmetry exists. The bands may not share a perfect center. Some bulge to one side, some collapse at the edge. But the density of the layering remains. This is what distinguishes Laguna Agate from others. Not randomness, but concentration. The locality is narrow, Ojo Laguna, in northern Chihuahua, Mexico. For decades, it has produced agates that cutters and collectors regard as reference specimens. The color palette is consistent, saturated reds and oranges, bordered by whites and pale grays. Few other agates maintain this intensity across such a multitude of delicate layers. The process is slow. Each band represents a phase of deposition, silica entering, depositing, and halting. Iron oxides introduce reds. Other trace elements shift tones to orange or pink. Over time, the void fills. When cut, the polished face shows a complete archive of interruptions. Some nodules produce open centers, cavities lined with quartz crystals. Others seal entirely, layer upon layer, until no void remains. The outer rind is dull, unremarkable. Only cutting reveals the inner structure. Laguna Agate gained widespread recognition in the mid-20th century as collectors in North America and Europe sought the most vibrant examples of banded agate. Its reputation has remained. Dealers often describe it as the most colorful or most finely banded of agates. The terms are relative, but the consistency of the material lends support to them. Each specimen differs. Some bands are razor thin, others widen. Some shift color abruptly, red to white in a single step. Others fade gradually, but the rhythm remains layered, repeating, precise. In the market, Laguna Agate commands higher prices than most agates, not for rarity of occurrence. Agates are common, but for rarity of quality. Few other localities yield nodules with such fine, saturated, and stable banding. Collectors treat the stone as both a geological specimen and an aesthetic object. Some slabs are cataloged in drawers, labeled with locality, date, and dimensions. Others are cut into cabochons, set in jewelry not for brilliance, but for pattern. Viewed closely, the lines do not blur. The boundary between one band and the next is sharp. The eye moves from red to white to orange with no gradient. Each band is discrete. Each one marks a stop, then a start, and the sequence continues until the cut stops. Ranked third, Kambaba Jasper, fossil stromatolites from the Precambrian. Before there were animals, before plants, even before oxygen filled the air, mats of microbes spread across shallow seas. They grew in layers, capturing sunlight and slowly altering the planet's chemistry. What remains of them today is preserved in a stone called Kambaba Jasper. The material looks dark green, streaked with black orbs and swirls. To the collector, it is a striking pattern. To the geologist, it is a fossil archive. Each orb, each loop, is the mineralized trace of stromatolites, colonies of cyanobacteria that lived more than 2 billion years ago. Cyanobacteria were among Earth's earliest life forms. They bound sediments together, secreted sticky films, and built dome-like structures in shallow water. Over immense spans of time, these mats trapped layers of silica and carbonates. Eventually, heat and pressure lithified them into stone. The circular shapes we see today in polished Kambaba Jasper are cross-sections of those ancient microbial colonies. The age is staggering. Dating places many of these specimens between 2.0 and 2.5 billion years old, well into the Precambrian. This was the time of the Great Oxidation Event, when cyanobacteria released oxygen as a byproduct of photosynthesis, thereby shifting the atmosphere from anoxic to oxygen-rich. Without these organisms, complex life could not have followed. Modern deposits come from Madagascar and South Africa. When cut and polished, slabs reveal concentric black-green rings, orbs merging into one another, sometimes stretched into irregular streaks. No two slabs are alike. Each reflects the uneven growth of microbial mats shaped by tides, currents, and sediment supply. In trade, the stone is labeled as Kambaba Jasper, although its composition differs from that of common jasper. It is microcrystalline quartz mixed with amphiboles, feldspar, and iron-rich minerals. The products of microbial structure replaced and stabilized over geological time. The term jasper is a commercial shorthand, not a strict mineralogical term. The patterns are dense but never perfectly symmetrical. Some surfaces are filled with tightly packed circles, edge to edge. Others show broad green fields with scattered orbs. Under magnification, one can trace the outlines of microbial laminae, layered like growth rings in an organism that was never individual, only collective. For collectors, the value lies in color contrast and polish. For scientists, the value lies in evidence. A few stones used in jewelry or decoration also serve as primary data for Earth's earliest life. Kambaba Jasper does both. Unlike transparent gems, it does not refract light. Unlike opal, it does not play with angles. Its meaning comes not from visual effect, but from temporal depth. The swirls are not designs. They are survival, recorded in stone. Culturally, it carries no myths. No temples recorded its use. Its significance is modern, understood only when science uncovered its origin. What was once seen as unusual green jasper is now recognized as a fossil stromatolite. Each polished slab is a page written by microbes, read by geologists, collected by enthusiasts. Each page is incomplete, but together they form one of Earth's oldest archives. Ranked second, plume agate, mineral sprays suspended in quartz. Inside the translucent body of plume agate, shapes rise that are neither crystal nor fracture. They branch, spread, and taper, like frozen currents. Each one is a plume, not organic, but mineral inclusions suspended within quartz. The background can be clear, milky, or tinted. Against it, the plumes stand in sharp relief. Some appear as golden sprays, others black needles. Still others, red or orange bursts. They are not patterns cut into the surface. They are three-dimensional structures grown inside the stone, revealed only when sliced. Geologically, they form when silica solutions, carrying trace elements, infiltrate volcanic cavities. As the silica gels solidify into chalcedony, mineral impurities precipitate. Iron produces reds and yellows, manganese, blacks, titanium, whites. The inclusions expand along diffusion fronts, branching as conditions shift. Once quartz hardens, it is fixed, permanent, and visible only by cutting through it. Different localities yield different appearances. Oregon's plume agates are renowned for their distinctive orange and yellow sprays. Mexico's Chihuahua district produces sharp black and red plumes in clear hosts. Madagascar offers softer greens and blues. Each deposit provides its own palette, shaped by local geochemistry. The stone does not refract or display optical effects. Its appeal lies in the illusion of depth. A good specimen holds a miniature scene, a thicket, a burst of flame, a cloud suspended midair. Yet these are not images. They are deposits, random, uncontrolled, and final. For cutters, orientation is critical. Slice one direction, and the plume appears dense, almost opaque. Slice another, and the same inclusion stretches, diffuses, or vanishes into haze. No two cuts from the same nodule are alike. This variability is why plume agate is prized, not for uniformity, but for unpredictability. On the market, collectors seek contrast, intense colors, distinct plume forms, and transparent quartz backgrounds. Cabochons may display a single isolated spray, floating in transparency. Slabs may show entire clusters, layered like multiple exposures. Value comes not from carat weight, but from the strength of the scene. Unlike banded agates, which archive repetition, plume agate resists sequence. It presents snapshots. Each specimen is a frame cut from an event that never repeated. There is no rhythm, no cycle, no symmetry. Only branches and dispersals stopped in progress. Culturally, the stone has no mythic record. Its significance is modern, born from collectors and lapidaries. Its identity is descriptive, not symbolic. Viewed closely, the inclusions show granularity. The edges are not smooth. They dissolve into the host at their margins. The plumes are sharp in some zones and blurred in others, revealing how deposition conditions shifted during midgrowth. A single polished cabochon can display multiple states at once, a defined red plume at one end, fading into a ghostly yellow blur at the other, and the image stops there. In first place, zebrastone, Precambrian stripes of iron and clay. Zebrastone does not display motion. It displays repetition. Parallel bands, red, brown, and cream, alternating across flat surfaces. Each stripe is discrete. Each stripe is the same. Geologically, this is composed of claystone and siltstone, deposited approximately 600 million years ago. The alternating colors originate from shifts in mineral content. Hematite-rich layers form the red-brown, while silica-rich layers form the pale cream. The banding is not decoration. It is a sedimentary rhythm, a record of environmental cycles that repeated long enough to build entire beds of striped rock. Unlike agates, which exhibit banding that follows cavities and curves, zebrastone maintains its lines in a straight line. The surface does not spiral, does not branch. It runs parallel like pages of a book, closed and compact. The locality is singular. Zebrastone is found only in the East Kimberley region of Western Australia. No other deposit has produced identical material. The host rocks are part of the Proterozoic basin, a sequence laid down before animals diversified, before shells evolved, and before complex life forms appeared. The stripes you see were present when multicellular organisms were beginning. The appearance is uniform but not featureless. Some blocks show wide bands, centimeters thick. Others, narrow lines, stacked tightly. The rhythm varies, but the direction remains the same. The eye can follow one stripe across a polished slab without interruption until it vanishes at the edge. Cutters and collectors work with what the rock offers. It does not refract light. It does not reveal hidden cores. Its value is in exposure. A slab polished flat presents the bands as they are, without any alteration. The uniformity is the identity. In commerce, zebrastone is carved into geometric objects, spheres, or tiles. But each cut is only a sample, a fragment of a much larger formation. The bands continue beyond the slice, uninterrupted, unseen. The science is precise. Zebrastone's age places it near the end of the Proterozoic eon, approximately 600 million years ago. It records quiet intervals of deposition in shallow water, during which iron levels in the sediment fluctuate, leaving alternating layers. Each change was minor, incremental. Over time, they built a striped archive across the basin. There is no myth associated with the zebrastone. It does not feature in ancient rituals. Its significance is modern, understood as both a geological specimen and an aesthetic material. But its more profound importance is as a stratigraphic witness. It shows us how regular, small processes can accumulate into formations, measured not in meters but in eras. Viewed closely, the boundary between one band and the next is abrupt. No gradient, no blending. The iron stops, the silica begins, over and over without variation. The observer might ask what lies beyond the polished face. The answer is more of the same. Lines that continue, unseen across the block, across the bedrock, across time. And then they stop, not here, not in view, but somewhere further in the stone, where the slice did not reach. The sequence ends where it began, not with brilliance, not with perfection, but with records left inside stone. Each pattern shown was accidental, unplanned, and unrepeated. Circles that were once microbial mats, stripes that were once sediments, plumes that were once mineral intrusions, webs that were once fractures. No stone was unturned. They only held what time allowed and stopped. The archive closes here. Let us know which one resonates with you in the comments, and don't forget to like and subscribe to our channel for more content like this.